Primitive forms of data networks have a long history, including the smoke signals used by primitive societies, and certainly including 19th century telegraphy. The messages in these systems were first manually encoded into strings of essentially binary symbols, and then manually transmitted and received. Where necessary, the messages were manually relayed at intermediate points. A major development in the early 50s was the use of communications links to connect central computers to remote terminals and other peripheral devices, such as printers and remote job entry points. The number of such peripheral devices expanded rapidly in the 60s with the development of time-shared computer systems and with the increasing power of central computers. With the proliferation of remote peripheral devices, it became uneconomical to provide a separate long-distance communication link to each peripheral. Remote multiplexers or concentrators were developed to collect all the traffic from a set of peripherals in the same area and to send it on a single link to the central processor. Finally, to free the central processor for handling all the communication, special processors called front ends were developed to control the communication to and from all the peripherals. This led to the more complex structure shown in Figure 1.2. The communication is automated in such systems, in contrast to telegraphy, for example, but the control of the communication is centrally exercised at the computer. While it is perfectly appropriate and widely accepted to refer to such systems as a data network or computer communication network, it is simple to build with as a computer with remote peripherals. Many of the interesting problems associated with data networks, such as the distributed control of the systems, the relaying of messages over multiple communication links, and the sharing of communication links between many users and processes, do not arise in these centralized systems. The ARPANET and TimeNet, introduced around 1970, were the first large-scale general-purpose data networks connecting geographically distributed computer systems, users, and peripherals. Figure 1.3 shows such networks. Inside the subnet are a set of nodes, various pairs of which are connected by communication links. Outside the subnet are the various computers, databases, terminals, etc., that are connected via the subnet. Messages originate at these external devices, pass into the subnet, pass from node to node on the communication links, and finally pass out to the external recipient. The nodes of the subnet, usually computers in their own right, serve primarily to route the messages through the subnet. These nodes are sometimes called IMPs, or interface message processors, and sometimes called switches. In some networks, for instance DECnet, some of the subnet nodes can be implemented within the computer using the network. It is helpful, however, to view the subnet nodes as being logically distinct from the computers outside the subnet. It is important to observe that in figures 1.1 and 1.2, the computer system is the center of the network, whereas in figure 1.3, the subnet, that is, the communication part of the network, is central. Keeping this picture of external devices around a communication subnet in mind will make it easier both to understand network layering later in this chapter and to understand the issues of distributed network control throughout the text. Since 1970, there has been an explosive growth in the number of data networks. These networks will be discussed later, including the seminal ARPANET and TimeNet networks, but for the moment Figure 1.3 provides a generic model of data networks. Before data networks are examined, a brief overview will be given first of the technological and economic factors that have led to network development, and second, of the applications that require networks. The major driving force in the rapid advances in computers, communications, and data networks has been solid-state technology, and in particular, the development of very large-scale integration, VLSI. In computers, this has led to faster, less expensive processors, faster, larger, less expensive primary memory, and faster, larger, less expensive bulk storage. The result has been the lowering of the cost of computation by roughly a factor of 2 every 2 years. On the other hand, with the development of more and more powerful microprocessor chips, there has been a shift in cost effectiveness from large timeshare computer facilities to small but increasingly powerful personal computers and workstations. Thus, on the one hand, an increasing number of applications can be computerized at a reasonable cost, and on the other hand, the primary growth is the number of computer systems rather than in the increasing power of a small number of very large computer systems. The above discussion of computational costs neglects the cost of software. While the art of software design has been improving, the improvement is partly counterbalanced by the increasing cost of good software engineers. When software can be replicated, however, the cost per unit goes down inversely with the number of replicas. Thus, even though software is a major cost of a new computer system, the increasing market decreases its unit cost. Each advance in solid-state technology decreases the costs and increases the performance of computer systems. This leads to an increase in market, thus generating decreased unit software cost, leading in a feedback loop to further increases in market. Each new application, however, requires new specialized software, which is initially expensive until a market develops, and which requires a user learning curve. Thus, it is difficult to forecast the details of the growth of the computer market and similarly of the data network market. The cost of transmitting data on a communication link from one point to another has also been dropping, but at a much slower rate than computational costs. The cost of a data link increases with the available data rate, but the increase is much less than linear in the data rate. Thus, the cost per transmitted binary symbol decreases with the data rate of the link. It is often economically advantageous for many users to share one hybrid data link rather than having separate data links for each. This effect is seen in figure 1.2 with the use of multiplexers and concentrators to share communication costs. One result of sharing high-speed, that is, high data rate communication links, is that the cost of sending data from one point to another increases less than linearly with the geographic separation of the points. This occurs because the communication path could include a short link to a shared long-distance high-speed link, and then another short link to the destination. Estimating the cost of a transmission facilities is highly specialized and complex. The cost of a communication link depends on whether one owns the facility or leases it. With leasing, the cost depends on the current competitive and regulatory situation. The details of communication costs will be ignored in what follows, but there are two overall effects of this cost that are important. First, for wide area networks, the cost of a network is presently dominated by transmission costs. Second, for local area networks, the cost of a network is not dominated by transmission costs. Coaxial cable and even a twisted pair of wires can achieve relatively high-speed communication at modest cost.